Hey, so I recorded this like yesterday and it was 22 minutes long. So I tried to take out a few slides, couldn't take out much because I lost some of my information. But I'm going to just try to like go over some of these slides, and I'll also send you the PowerPoint for things I don't cover as much just because of time. Okay, so my presentation was on the classification of smokeless powders using laser electrospray, mass spectrometry, and offline multivariate statistical analysis. Sounds like a lot, but I'll explain it. So you got a problem? We needed a discrimination of ammunition and forensic science because it was one of the more analyzed topics due to the prevalence of firearms and criminal activities. So we need a technique that is needed to rapidly identify and discriminate the firearm ammunition and gunshot residue to help with the crime scene analysis. We need one that has high sensitivity, the capability to detect both thermally liable and volatile compounds, as well as can provide rapid analysis of each sample without a time-consuming sample preparation. So I want to talk, I'm not really going to hit on this much, but this is just the components of GSR, which it's mainly composed of the combustion products, unburned primer, as well as the powder components. We're going to really be focusing on the propellants, which is the chemical that allows the bullet to go through or get pushed out of the barrel. We're going to focus mainly on smokeless powder. There are two common propellants, which is black powder and smokeless powder, but we're going to focus mainly on smokeless powder. So, smokeless powder. That's what we'll be examining with the LEMS, which is the laser electrospray mass spectrometry. This will help us discriminate the different types of GSR. And then I'll talk about the different classes. There's three classes. We have single base, which is cellulose nitrate. We have double base, which is cellulose nitrate, as well as nitroglycerin. We have triple base, which is cellulose nitrate, nitroglycerin, and then nitroguanidine. So these different smokeless powders, the manufacturers add different, energetic components to the propellant in order to change its physical capabilities, such as the stabilizers, the plasticizers, the flash suppressions, deterrents, the opacifiers, all of those things to help change physical capabilities. But these different components helps aid in the discrimination, so we can distinguish whether it's a single, double, or triple base powder. So additives. These are added in order to help tailor the weapon. We have several different additives. We have DNT, which helps prevent the secondary flash at the muzzle of the weapon. We have DMPD-BP, which is a plasticizer. We have carbon black, which is an opacifier, and that helps ensure that there's a reproducible burn rate. We have the ethyl-methyl centralite, which is what we'll focus on a lot during this presentation. These are added with the nitrous oxide, which is the decomposition of nitrocellulose, and that allows for the stabilization of the composition. These are added in different concentrations, which also allows us to be able to differentiate the three classes of smokeless powders, which I discussed with single, double, and triple. So with that being said, we need a technique that can help detect these different compounds, but because they're used in so many normal everyday use cleaners, there's only two that actually confirm the presence of a smokeless powder that provide evidence that it is indeed GSR, and that is the ethyl centralite and the methyl centralite. So what technique do I use? Previously, a few things, I'll just mention a few because I won't go through it all. They've used GC, HPLC, TLC. They've used IMS, which is what we'll be using, ESI, DESI, NESI, MS, and then Raman. Still went through all of them. So we're going to choose ion mobility spectrometry. We'll choose this because there is some sample preparation, but not a lot. The only downfall is that the interference may produce false positives and false negative results. But this analytical technique can detect organic stabilizers, which most smokeless powders contain. Yeah. So on this slide, I just discussed a few methods that could be problematic. I chose GC and LC coupled with mass spec. because GC, first of all, the hot temperatures can cause thermal degradation in the sample, and that'll increase the reactivity with the analytes, which will therefore skew the results. LC has a wide range of polarities, and because we have several of these different compounds in each smokeless powder, that becomes problematic. ESI hasn't really shown the ability to be able to detect these different stabilizers and plasticizers at the same time, which makes that also problematic. And then Raman, it does exhibit bands that correspond to the ED, DNT, and DPA, but it has a lack of detection for plasticizers, which eliminates that as a method choice as well. So we're going to talk about LAMS, which is the laser electrospray mass spectrometry. It was developed to perform direct analysis of complex mixtures without sample preprocessing, so we can eliminate that whole step of doing of the sample preparation with this technique. It can detect different classifications of explosives, inorganic salts, and then high explosives. So how is it used? The LMS couples with the non-resonant femtosecond laser vaporization, which uses electrospray ionization mass spec, and then the femtosecond laser vaporizes all of the analytes. Next is followed by capture, then ionization, and then it transfers all of those pieces into the mass spectrometer, which is read with the electrospray cone. So during the experiment, what we're going to have is the 5 different smokeless powders investigated in the experiment. We have 2 Remington powders, 1 Alliant Tech Systems powder, a Hornby powder, and then a high-grade smokeless powder. So the sample preparation, they took each of the samples, removed them from the cartridge directly prior to the analysis. They spread it evenly on a double-sided piece of tape. And then the tape was pretty much to ensure that the powder was not able to move while they did the vaporization. And then the sample plates were placed on a staged sample, which was then entered into the ESI source chamber. Each sample plate was supported by a 3-dimensional translation stage, which allowed the fresh sample to get hit with each laser shot. And then the sample plate was raster scanned with the incident laser fired at 10 hertz. And then at least 10 mass spectra were collected for each powder sample. So they had a good amount of data for each set. So the laser vaporization ionization. LEMS is used as it was explained previously, but briefly. The system combines the femtosecond laser and is used to induce the non-resonant vaporization of propellant components into the gas phase with the ESI source for capture, and then ionization of the vaporized material occurs. Below is what they use to generate this laser. It's a titanium sapphire laser oscillator, which generated a 300 milliwatt beam, which was centered at 800 nanometers that seeded the regenerative amplifier to create the 2.5 mil 70 femtosecond pulse, synchronizing with the ESI source. Won't go in too far into depth because of time, but I'll send you this. So the mass spectrometry involved, the ESI consisted of a stainless steel electrospray needle, a dielectric capillary, and then a skimmer, as well as 2 hexapoles. The electrospray was maintained at ground with the capillary inlet. It was biased to about negative 4.5 kilovolts to extract the positive ions from the sample. And then the vaporized analytes were captured using the electrospray solvent, which was about 1% acetic acid to a 1-to-1 ratio of methanol and water. And then there was a flow rate of about 3 microliters per minute that was set by the syringe pump. So the first hexapole was operated into the trapping mode, where the positive ions collected from the ESI, it was sent there and it was collected for about 250 microseconds, and then after it exited the first hexapole, it was then transferred to the time of flight extraction region, where it occurred, or where it ran into the second hexapole. So some more mixed mass spectrometry. Once it exited once it was in the extraction region, the 2 high voltage pulsars that were that triggered, which injected the ions into the time of flight analyzer. So then all of the positive ions were detected after the TOF analyzer was used, and then they were averaged using the digital oscilloscope for the LEMS analysis. And then the smokeless propellant samples were subjected to the the femtosecond laser pulse, which resulted in the vaporization, and that also gave us more mass spectrum data. Like I said before, 10 mass spectrum were averaged per powder sample. We obtained our background by vaporizing just the double-sided tape without any powder at the beginning of the experiment. Now, because the EC and the DPA from the smokeless powders is a extremely high volatile compound, they did show up on the mass spectrum, but they were able to subtract the peaks because EC and then the DPA were known peaks, and they were able to subtract those to get the actual background. So some of the safety considerations, like I explained previously, each of the powders were not released from their cartridges until directly prior to the LIMS analysis. They were all sequestered by Bren, and then they were stored at dry locations. Because lasers were used, laser eye protection was worn at all times, and then anything dealing with the high voltage was closed and then closed to prevent the accidental contact with the electrodes. So, detection of organic stabilizers, we already discussed that LIMS was used to detect the 5 powders. I'm gonna have to skip through this because I'm running low on time, but the LIMS spectrum suggests that EC is the main distinguishing ion in the composition that for sure lets you know that a smokeless powder was being used. Also, another huge stabilizer which was found in the data was the DPA, which is diphenylamine. That stabilizer was detected in the Remington pistol, the Hornady pistol, the high-grade powder, and then the Remington rifle, but not in the federal powder. The only thing that was found in the federal powder was the ethyl centralite. The DPA byproduct, which is 4-NDPA, was detected in the high-grade powder using the LIMS mass spectrum analysis. Here is the powder analysis with the different stabilizers, plasticizers, each component that allows you to tell you or differentiate which powders were being used. It's really hard to see, but there's plus and minus signs to indicate if it liked it or if it composed it. So the different plasticizers, we got dibutylphthalate. That was found in the smokeless powders, and it was protonated, but they were able to tell that using the nano electrospray ionization. The Remington pistol and the high-grade smokeless powder displayed this DBP in low concentrations. So there were a bunch of identified peaks in the LIMS analysis, and this it cannot be determined whether the peaks were adducts, fragments, or clusters the image, like just tandem mass spec by itself, couldn't determine whether if it was adduct, a fragment, or a cluster of the powder. That's why they had to do more analysis, but it also led to further discrimination because they all didn't produce the same mass spectra. So we know that the detection of DPA or DBP does not confirm the presence of a smokeless powder, only the EC and MC, which I discussed. Very briefly, they use the MATLAB because I'm passing my time. Really quickly, they use MATLAB. They use a transform data set using the mean adjusted training set, and the training set was just 3 randomly selected mass spectrum, and then the rest of the remaining mass spectrum were used as the testing set. The coefficients obtained from the training set were multiplied by the mean adjusted testing set, and this was just to determine. This was another analysis to determine different smoke powder, the different smokeless powders, as well as aid in the discrimination. So the PCA load-in plots indicated that EC was an important signature, which we've already discussed, and how you knew that was because the EC had a positive loading value. As explained further, the ones with negative loading powders exhibited DPA, NO, DPA, DMP, and DPA alpha. So to take into consideration, so I can wrap this up, there were multiple other experiments done, which allowed the current researchers to use that data compared to theirs and further confirm what what knowns and unknowns were in each of the smokeless powders. So using that prior experience, they were able to tie that in with theirs and also build on it because they were able to find these different unknowns, test them, and figure out what they were. So they were able to add that into the analysis. The conclusion. The LEMS measurements of the 5 different ammunitions revealed the distinct chemical makeup of each smokeless powder. So we were able to clearly detect what components were in each of the powders. The use of the training set and the 3 mass spectra from each powder, which I said was the PCA analysis, that allowed classification of the rest of the measurements using what was called the K-nearest and the linear discriminant analysis. And then the LAMS analysis also determined the manufacturer of each powder that we analyzed. As far as the analysis, they said that if they had more techniques that require more time and sample preparation, they will also be able to tell what kind of bullet as well as what firearm was used using the, what I just said, the different analytical techniques. Because we used the LEMS method, it was very, very, very fast, and then it had minimal sample preparation, which couldn't be compared to something that would take more time as well as something that had more sample preparation. All right, that's it.